The final topic for section 5 has to do with the widths of the lines and the physics behind them. In principle, we expect that emission and absorption lines will result from quantum physics, and therefore they will be incredibly well defined. If you think about it, you'd probably expect lines to be infinitely thin, sort of a direct delta function. In practice, these lines are not just direct delta functions, and they can be actually very broad. In 263, what we're going to cover are these three different aspects of how you can actually broaden a line, and they're actually ordered in terms of importance. And if you can't wait for the rest of the videos, you can already have an idea, a glimpse into how important the different effects are. And it turns out that quantum broadening doesn't really do much at all. We can't even see it here. It's still broadening the line, but it's really negligible. After that, actually, thermal broadening matters more, and it will matter even more at higher temperatures. But it turns out that, at least in a wider astrophysical context, rotation will be the most important driver of making lines very broad. Quantum broadening essentially originates from the Heisenberg uncertainty principle, essentially the fact that energies can never be determined with infinite precision. If you follow the steps, just like in the lecture notes, this is not so relevant because it turns out that quantum broadening doesn't really affect astrophysics at all, but you can very easily deduce an expression for quantum broadening. This will depend on the wavelength of your transition, but most importantly, it will depend on sort of the lifetime of your transition, or how much time you need to wait for the electron to transition down, and therefore for you to get the photon. What happens is, for almost all cases, these excited states last for so little, essentially something like 10 nanoseconds, then when you calculate this, you realize that the broadening is incredibly small. So we're talking about something like 10 to the minus 5 nanometers. The important message here is that even though we can determine quantum broadening very well, and we can link it very nicely to the Heisenberg uncertainty principle, in reality, this quantum broadening that you can see here is incredibly small. And even just a temperature of 1 Kelvin will mean that thermal broadening will already dominate. Thermal Doppler broadening actually comes about from the fact that with temperature, then your particles or your atoms will actually be moving around. We can think about the typical velocities. In practice, the average speed of a gas will depend on the temperature and also on the composition. Because it depends on the composition, it means that if you're looking at atoms that are much heavier, they will actually be moving much slower than if you're looking at a gas that's made of very light elements. The distribution of speeds can be very well described by the Maxwell-Boltzmann speed distribution that you can see here. And we can use the most probable value given by this, essentially square root 2 times Boltzmann constant, temperature over the mass, the typical mass of your particles or the atoms that make up your gas. And this means that if you use the Doppler effect, then you can actually translate this typical velocity or the most probable velocity into a shift in wavelength. And if you do that, you realize that this shift in wavelength will depend on the wavelength you're looking at, but also on temperature. And because of the dependence on mass, it will also depend on what the gas is made of. And this is if you look at something like the 1 sigma broadening, if you're actually looking at sort of the width at 50%, or the full width of half maximum, this is what you'd be calculating. Thermal broadening is way more important than quantum broadening, but even at something like 6,000 Kelvin, sort of the temperature of the sun, then the broadening is actually still very, very small. We're just looking at something like 0.04 nanometers. Finally, it is important to notice that whenever you have some thermal velocities, you can also have turbulent velocities that can be caused by many physical phenomena. And a way to combine that is to simply add it as some sort of turbulent velocity in quadrature to the equation that we derived before. However, as we'll see, and you can find further details also in the lecture notes and in this plot right here, even though thermal broadening can be quite important if the temperature is very high, for the typical velocities, for example, rotation velocity of some stars, or even how stars rotate around galaxies, when you look at the integrated spectrum, that will lead to some broadening of the lines. And very easily, rotation will be the dominant source of broadening when we take a spectrum of a star or a galaxy. And this is a specific example where we have a star of 9,000 Kelvin. We can calculate what is the typical thermal velocity we would expect, and also the rotational velocity. And this obviously implies that rotation will be the dominant source of broadening if we were to take a spectrum of the star.